Thank you, Mr. Chairman. Good afternoon to everybody. I'm Lieutenant Colonel Fabrizio De Paulis from the Flight Test Center of the Italian Air Force, and I'm going to show you an example of a real failure analysis carried out by my group, in this case with a contribute from the Materials Engineering Department of the Roma University La Sapienza, and related to a failure occurred to an engine component of a military aircraft. As it usually happens in our job, the investigation was carried out with the aim of understanding, firstly, the failure root cause, in order to prevent other similar cases, and secondly, also to identify, if possible, some responsibilities. The agenda showed all the analysis and the exams we carried out, and basically the way we got our target. Well, let's start with our case. During pre-flight operation, a trainer military aircraft experienced an engine overspeed. In the aftermath, maintenance personnel performed the required operations, among which some non-destructive testing inspection of the engine crankshaft. And in particular, magnetic particles and liquid penetrant test found two cracks, both of more than about 45 mm long, and both located on the main bearing journal of the crankshaft, with one starting from a lubrication hole and a little bit longer than the second one. Moreover, a circular duct band compatible with an overheating phenomenon was also observed in the same region. And that's the reason why the system designer responsible, SDR, and most of all the original equipment manufacturer, OEM, attributed the crack's origin to an in-service thermal stress suffered by the crankshaft and followed by crack propagation due to a normal fatigue phenomenon. The investigation carried out at the Flight Test Center by my group allowed to establish the real origin of the fractures occurred to the crankshaft. Well, at the first, the part of the crankshaft interested by cracks was divided into sections to correctly open the cracks and to observe them. Crack number one started from lubrication oil, and inside the oil chamfer, a ducting area was observable, and visual examination showed also the typical features of a fatigue crack propagation. The side view showed also about a 45-degree orientation of the crack along the oil chamfer with respect to the crankshaft rotation axis. And at the optical microscope, the crack number one showed two different morphologies. The first one, characterized by bright and smooth grain and located at the intersection between the oil chamfer and the journal surface, is the initiation point of the observed fracture. And the second one is the typical propagation area with the typical features of a fatigue crack propagation, such as beach marks and ratchet marks. About crack number two, as visible, just as already visible from NDT test, this crack propagated on the opposite side with respect to the crack number one, and was differently oriented with respect to the crankshaft rotation axis, as you can see from these open fragments. And again, crack number two showed two different morphologies: the initiation zone morphology, that was a stripe of about 0.25 mm from the external surface of the crankshaft, and the typical propagation area. Moving to electron microscopy, the morphology of the initiation zone for both cracks showed a typical brittle rupture. For both cracks, the fracture took place starting from the grain boundaries, as you can easily see from this image. And furthermore, the transition between the initiation zone and the propagation area was sharp, moving from an intergranular morphology to a transgranular one without a smooth gradient. And in addition, electron microscopy confirmed the typical fatigue mechanism as shown by propagation region of crack number 1 and crack number 2. And allowed also to identify on the darkened area of the inner oil chamfer the presence of diffused iron oxides with a morphology compatible with the thermal oxidation mechanism. Finally, at the end of the fatigue region, electron microscopy showed typical dimples, characteristic of the unstable phase of the fatigue mechanism with a morphology, an overload morphology. Well, what do microfractographic evidence tell us till now about the failure mechanism? First of all, we have two cracks with a fatigue mechanism coherent with the normal engine cyclical load condition. Although the brittleness of the material and its consequent low plasticity ejection do not permit to obtain, to gain a lot of information about the frequency of the phenomenon. And probably crack number 1 started before the second one due to its major length. Moreover, the fact that we have observed thermal oxides, iron oxides, almost only on the fracture surface and not on the external surface of the crankshaft is attributable to an overheating phenomenon following and not preceding the crack growth, as was initially stated by the OEM. And about the initiation mechanism, probably this is attributable to an hydrogen embrittlement phenomenon due to the intergranular morphology, to the sharp grained boundaries, and the tidy and clear exposition of the crystal lattice. And this last element was confirmed by chemical analysis. So looking at the chemical analysis, plasma analysis confirmed a composition in accordance with the specification for AI SI 4340 steel, an alloy widely used for engine structural component. But we, moreover, performed an EDS mapping starting from the external surface of the crankshaft in order to measure the nitrogen content due to the nitriding process performed during the production process. And the results showed that nitriding process diffused nitrogen in a layer of about 500 microns starting from the external surface and decreasing towards the core. Finally, due to the strong intergranular morphology and looking for hydrogen content, we performed hydrogen content analysis on different parts of the crankshaft. And we found, for example, for the oil chamfer portion, for the oil chamfer portion, about 3 ppm and even 4 for the journal surface. An amount higher than the average for this alloy, about 1 ppm, and sufficient to significantly decrease its fracture toughness, about 50%, for this alloy. Moving ahead, the microstructural examination confirmed the martensitic structures for this steel, and also for the oil chamfer section confirmed the nitrogen diffusion in a layer of about 500 microns starting from the journal surface. And finally, micro-hardness figures tests were performed in order to analyze the microstructural variation due to the nitriding process. And the results revealed a considerable hardness gradient near the inner surface of the oil chamfer, and a very strong gradient for the crack number 1 section, for example, moving from the core about 400 HVU to more than 1000 HVU at the initiation zone of the fracture, in agreement with the enhanced brittleness of the zone. and with the morphology observed. The last part of our investigation included the finite element analysis performed just to have an idea and about the stress condition acting on the region of the cracks. So a 3D model was reproduced with a suitable mesh for the mathematical model. Then, being unknown the real load spectrum, the load conditions were obtained by calculation in a simple way, starting from obtaining the mean torque acting on the crankshaft from the mean engine power and the mean stress acting on each connecting rods from the torque itself. And so for each connecting rod we have a load condition. In this image, for example, we have the load condition 1 on the connecting rod 1. And for each load condition, a related stress map was obtained where the detail represent the stress, for example, around this lubrication hole. Obviously, 6 stress maps were obtained from the 6 load conditions with the position and the maximum principal stress value reported in this table. The important thing is that all these values are largely below the fatigue limit for the alloy, and only for the load condition number 2, oil chamfer is the zone with the maximum principal stress value. And this is the related stress map with the detail of the stress condition acting on the lubrication hole from which started crack number 1. So, let's explain the conclusion of our failure investigation, starting again from our initial target. Understand the real root cause of the failure. Well, first of all, crankshaft failed because of fatigue crack, whose initiation was facilitated by an hydrogen embrittlement of the material. The hydrogen embrittlement in this case in detail is attributable to a not sufficient or not proper backing treatment performed after the nitriding process to which the crankshaft is undergone during the production process. Moreover, the numerical model confirmed that the oil chamfer, the point from which one of the cracks started, the first crack started, is a stress concentration point, but its maximum value is largely under the yield stress for this material, and so only a decrease of the allowable fatigue limit for this material due to hydrogen embrittlement can be the cause of the crack initiation according to its morphology. And finally, the thermal stress observed was a consequence of the friction of the crankshaft due to the dimensional variation following the crack number 1 propagation, and this phenomenon likely induced crack number 2 initiation. And in any case, overheating was a consequence and not the cause of the fatigue mechanism. Thank you for your attention.